Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. This is the second lecture on calculus. In the previous lecture, we looked at derivatives, partial derivatives, and gradients. In this lecture, we are going to specifically look at the chain rule. And the chain rule is a simple rule, but it is the backbone. It is the backbone of an algorithm called as backpropagation. And backpropagation is the algorithm which helps us to optimize the weights of the neural network so that the loss is minimized. And at the heart of backpropagation lies the chain rule. It's a very simple rule if you understand what's going on, but if you just skim over the chain rule, and if you really don't understand the mathematics behind it, then quickly the math of backpropagation becomes difficult to master. But if you really understand the intuition behind the chain rule, then actually understanding backpropagation becomes really easy. So let me get started with explanation of the chain rule. So the way the rule works is as follows. Let's say I have a function z, which is a function of x, or rather let me start from y. So let's say I have a function y which depends on z, okay, and or which depends on z, and z in turn depends on x. So if you write these two functions in a combined manner, so y is equal to f of z, right, but z is equal to g of x, so y is equal to f of g of x. Now, here is where chain rule comes into the picture. If y was just equal to f of x, then calculating the derivative of y with respect to x becomes very easy. dy by dx is just f dash of x. But now there is one more layer between y and x. In this case, y is equal to f of g of x. So the real question is, how do we now find the derivative of y with respect to x? So we clearly see that y depends on x, right? But it depends on x through another function. So y is a function of something, and that something is a function of x. So that's why it's called chain rule. So we are essentially chaining two functions here. So we are chaining two functions here. We are chaining two functions, and we want to find the derivative of y with respect to the innermost variable, which is x. So let us see actually a practical example of this. So let's say you have a car, okay, and you are going from point A to point B. Let's say you are going from New York to California, and let's say the speed of your car is 60 kilometers per hour. What I really want to know is how much is the fuel consumption of my car vary with the time which the car travels. So this is very important, right? Because I need to plan for the fuel. So I want to know, if a small change in time, how much does it affect the fuel consumption? So if I call the fuel consumption as y in this case, and if I uh, call the time which the car travels x, I essentially want to calculate dy by dx, where y is the fuel consumption and x is the time. Okay. Now it turns out that the fuel consumption of the car depends on the distance. So it turns out that the car consumes 1 liter per 30 kilometer. So the fuel consumption actually y is a function of the distance z. And here we denoted that by f, right? So y is actually a function of z, and z is the distance, right? So in fact this function is just z divided by 30. because if Z is 30 kilometer, the answer will be 1 liter. If Z is 60 kilometer, the answer will be 2 liter. Remember, 1 liter is consumed per 30 kilometer. So if the number of kilometers is X or Z, the fuel consumed will be Z by 30. So here's a problem, right? You wanted dy by dx, but it turns out that y, which is the fuel consumption, does not depend directly on time, but the fuel consumption depends on the distance. Then you are thinking, okay, if fuel consumption does not depend on time, how do I find the derivative of fuel consumption with respect to time? But you have a lifeline here, right? Fuel consumption actually depends on the distance. So fuel consumption depends on distance. So if somehow you can find a relation between distance and time, then fuel consumption can be related to time. And it turns out that since the car travels at a speed of 60 kilometer per hour, the function between distance and time is very easy. So Z is just so Z is g of x. Let me check if the notation is correct over here. Yeah, Z is g of x. So Z, which is the distance. So let me write it over here actually to make it clear. So this dependent Z is g of x, which is 60 into x. Remember, x is the time and z is the distance. So the fuel consumption which is y. So the fuel consumption which is y. Let me write it here again. Depends on the distance which is z, and z depends on time which is x. So the function connecting y and z is f, and the function connecting z and x is g. Now I want to find the derivative of y with respect to x. Derivative of y with respect to x. Right? So I essentially want to find derivative d by dx of f of g of x with respect to x. Remember y, so let me make it more clear. So y is f of z, which is z by 30. So this is f of z. And what is z? Z is g of x. So we are essentially finding derivative of f of g of x. Remember, this is exactly the premise which we started with in the lecture. We want to find the derivative of d by dx of f of g of x. So this is where the chain rule actually comes into the picture. The chain rule actually says that uh, okay, since you cannot directly take the derivative, the why don't you chain the things? So for example, the simplest way to visualize the chain rule is d by dx of f of z, right? So z does not depend on x. So we can write it as d by dz of f of z multiplied by dz divided by dx. Uh, and what is z? Z is equal to g of x. So z depends on x. So this will just be f dash of z multiplied by g dash of x. So simple way to think about the chain rule is that if you want to find the derivative of f of g of x, you first take the outer function and you take the dot, you do a dash operation, which means the derivative operation f dash, uh, and then you take the inner function and then you do its derivative into g dash. That's it. This is the answer. It's just that here it will be f dash and the variable will be z, so it will be a function of z and multiplied by g dash of x. So remember, f does not depend directly on x, but it depends on z. So this will be f dash of z multiplied by g dash of x. Let's see how this happens in practice. So f is now equal to, remember we have already seen these functions. F of z is z by 30. So f of z is z by 30. This means that f dash of z is just 1 by 30. And g of x is equal to 60x. So this means that g dash of x is just 60. So then the answer here would be f dash of z multiplied by g dash of x, which is equal to 1 by 30 into 60, which is equal to 2. Which means that dy by dx is equal to 2. And y was fuel consumption and x was time, which means 2 liters are consumed every hour. This is how you find the derivative with respect to uh, in a chain rule fashion. So this same thing which we did right now can be expressed in terms of a mathematical formula. So if you want to find the derivative of f of g of x with respect to x, first you find the derivative of f with respect to g of x, and then you take the derivative of g of x with respect to x. So this is just f dash of g of x, and this will be just g dash of x. So in the example which we saw, this is just z. So this will be f dash of z into g dash of x. And now remember, you can chain multiple functions like this together. So the advantage of the chain rule is that you can have how many ever functions you want. So let's say we have d by dx f of g of h of m of x. Remember the trick which I told you is start from the outermost function, take its dash, multiply by the inner function, take its dash g dash, multiplied by the function within h dash, and then finally multiply by m dash. And the variables just will be different. So m dash, so it will be m dash of x. This will be h dash of m of x. This will be g dash of h of m of x. And this will be f dash of g of h of m of x. That's it. So you just need to find the derivatives of each of these individual functions and then substitute the values of these quantities. And then you will get the derivative of the entire function with respect to the innermost variable, or df by dx. That's it. This is the chain rule which is at the heart of back propagation. We will take another example to motivate this idea further. So let's say we have an example h of x equal to 3 into 2x square raised to 5. So if I have given you this and I want you to find the derivative with respect to x, h of x, which means that I want you to find derivative with respect to x, 3 into 2x square raised to 5. So first thing to remember is that this is not an easy calculation because there are two functions involved. So you need to apply chain rule, but for that you need to first understand which functions are chained together. So the trick to doing that is that look at this inner function first. This is clearly looks like one function, right? So let me call this as g of x equal to 2x square. And so if you consider this as now z, if you call this as z, then h of x is just 3 into z raised to 5. So I will define one function g of x as 2x square, right? And I will define the second function f of z is 3z raised to 5. So then h of x, let me write this here. H of x then can be written as f of g of x. because f is 3z raised to 5 and z, uh, so f is 3 into z raised to 5, right? So f of g of x will be 3 into g of x raised to 5, and g of x is 2x square. So then f of g of x will be h of x. So now I'm asking you to find the derivative of h of x, which is d by dx of f of g of x. So then you can directly break it down to the chain rule formula, right? You first find f dash of g of x and multiply it by g dash of x. Okay. Now let us see what f dash and g dash are. So f of z is 3 into z raised to 5. So f dash of z will be 3 multiplied by 5z raised to 4, which is 15z raised to 4. And g dash of x will be derivative of 2x square, which will be equal to 4x. So the derivative of f of g of x will be f dash of g of x, which will be 15 multiplied by g of x raised to 4 and multiplied by g dash of x, which is just 4x. So the answer will be 15 into g of x raised to 4 multiplied by 4x. And what is g of x? G of x is just 2x square. So it will be 15 multiplied by 2x square raised to 4 multiplied by 4x. So that will be 960 into x raised to 9. This is the simple way to calculate the derivatives using the chain rule. Remember what we did here. So if you have a function like this, the first thing to identify is that this is a function which is created by chaining two functions together. And the way to identify which functions are chained is start with the innermost function. So we see 2x square, right? So then just replace this by a separate variable z. Then the outer function becomes 3z raised to 5. So then the inner function, let me call this inner. The inner function is 2x square, and let me call this outer. The outer function is 3z raised to 5. So then h can just be written as f of g of x. So then taking the derivative of h with respect to x simply means taking the derivative of f of g of x with respect to x. And that will be f dash of g of x multiplied by g dash of x. And remember, calculating f dash and g dash is very easy because those are just simple polynomials. So f dash will be just 3 multiplied by 5 times z raised to 4, and g dash will be 4x. Remember, if there is a polynomial ax raised to b, which is f, its derivative is a into b into x raised to b minus 1, which has been covered in the previous lecture. So then g dash of x is 4x and f dash of z is 15z raised to 4. So f dash of g of x into g dash of x will be 15 g of x raised to 4 multiplied by 4x, which will be 15 into 2x square raised to 4 multiplied by 4x, which is 960 x raised to 9. So that is the derivative of this function with respect to x. Now, why are we really doing this? Because the reason we are doing all of this is because if you take a neural network, right? If you take a neural network which looks something like this, there are multiple layers. This neural network essentially can be expressed something like y is equal to ReLU of W1 into of or ReLU of ReLU of ReLU of maybe W1 into X1 plus B1 plus uh, B0 multiplied by W2, something like that. So it will be a lot of functions which are chained together like this. So if you think of it in the formula or in the analogy which we just saw, this will be f of g of h of m of x. So if you want to take the derivative with respect to x, you need to apply the chain rule because there are a lot of functions chained together. So ultimately, we'll need to find the derivative of the loss function with respect to the weights, right? And if the prediction has this formula, then the loss function will also look like a multiple number of functions which are chained together. So to find the derivative of the loss function with respect to the weights, we will need to find the derivative of f of g of h of multiple functions like this. So that is why you need to really understand what the chain rule is and how it is implemented. Okay, so this brings us to the end of this lecture. Remember, at the end of the day, chain rule is very simple. Just remember this trick. If y is f of g of x, then dy by dx is just f dash multiplied by g dash. That's it. You start with the outer function, take its derivative f dash, then multiply it with the inner function derivative. And that way, if you keep this trick in mind, no matter how many functions are chained together, start with the outer, do f dash, then go to the inner, then do g dash, then go inner, finally reach the end. That's how you can multiply different derivatives together. Thank you so much, everyone. And I hope you have understood this calculus part, which has been covered in this lecture and the previous lecture. Starting from the next lecture onwards, we'll be directly looking at back propagation. Uh, so, thank you, everyone, and I'll see you in the next lecture.